In this video, we're going to go through overall polarity of a molecule. Let's start with the definition of polarity. Polarity is the separation of charge due to the unequal sharing of electrons. So this results in a partial positive and partial negative pole, and we call that a dipole. So if you think about where you've heard the word polarity before, if you think about the Earth, right, we've got the North Pole and the South Pole. Magnetic North Pole and magnetic South Pole. On a battery, for example, right? We've got our battery here. You've got a positive end and a negative end of the battery, right? So they're different sides. Okay, things are different at the North Pole than the South Pole. I mean, Santa Claus lives at the North Pole, and I think Superman lives at the South Pole, or maybe penguins. I'm not sure, but they're different. Okay, so that's the point that I'm trying to make with polarity. All right, so let's look at what polarity means in terms of Lewis structures. So when we draw our Lewis structures that are symmetrical are nonpolar. So if you look at the first example, everything attached to the central atom is the same. We only have hydrogen attached to the central atom, so it's symmetrical. It's nonpolar. It's the same. If you look at the second example, we don't have a central atom, but they are both chlorines. So if you think about this in terms of a tug-of-war, if I was doing a tug-of-war with my evil twin, we would be pulling in opposite directions with the same amount of force, and they cancel each other out. So if I was pulling in this direction with a force of 10 newtons, and my evil twin was pulling in the opposite direction with a force of 10 newtons, we cancel each other out. So that's how nonpolar works. Polar is a difference. So in the first example, we have hydrogen, 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 and then we have a chlorine. So they're not all the same. So that would be asymmetrical, and it would be polar. In the second example, we have our tug-of-war. So this might be doing a tug-of-war with somebody that is a lot stronger than me. One side's going to be stronger than the other. It's an unequal force. So in the terms of polarity, we have poles. One side is going to be more electronegative than the other. It's going to have a stronger pole. The last thing that can end up changing polarity are lone pair on your central atom. So if you ever have dots or lone pair on your central atom, that indicates polarity. So just to recap, we have our first example where everything attached to the central atom is not the same. It's asymmetrical. In a case where we just have two atoms, they're not the same. Think about a tug-of-war. And then in the third example, we have lone pair on the central atom. That indicates polarity. So let's do some examples. We're going to review Lewis structures as we also look at polarity. So it says predict the polarity of BH3. So we're going to begin by counting up our valence electrons. Okay, so boron has 3, hydrogen has 1, and there are 3 of them. So if I add those up, I end up with 6. Boron's by itself, it's going to go in the middle. I'm going to surround it with hydrogens. Now boron's a special case. Boron does not need 8 valence electrons to be happy. It only needs 6. So our next step is to bond everything to the central atom. 2, 4, 6. And we're good. So each hydrogen is getting 2 from the single bond. Boron gets 2, 4, 6 from all the single bonds. So it's happy. Now, everything attached to the central atom is just hydrogen. Okay, we only have hydrogen attached. There are no lone pair of electrons on boron, so this would be nonpolar. All right, let's take a look at the next one. So we've got phosphorus. We have fluorine. Phosphorus is 5. Nope. Yes, 5. Fluorine is 7, and there are 3 of them. 7 times 3 is 21. 26 total. Okay, phosphorus is by itself, so it's going to go in the middle, and then we're going to surround it with fluorines. Connect everything with a single bond. 2, 4, 6. And then let's start placing our lone pairs. So each fluorine has 2 from the bond. It needs 6 more. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. And then I have 2 more. Those are going to go on the phosphorus. Okay, so phosphorus gets 2, 4, 6 from all the single bonds. It needs 2 more for a lone pair. Everything attached to the central atom is the same, so it passes that check. But we have a lone pair of electrons. So because we have a lone pair of electrons on our central atom, that means this will be a polar molecule. All right, let's do CO2. Got carbon, oxygen. Carbon is 4. Oxygen is 6. And there are 2 of them. 6 times 2 is 12. 4 plus 12 is 16. Carbon always goes in the middle. 2, 4 bonding. I have 12 left. So let's start to place those on our oxygens. I can give each oxygen 6. 6 times 2 is 12, so I've placed all of mine. Carbon is not happy though. So carbon needs some extra electrons because it only has 4. So let's take 2 from here and draw a double bond. And let's take 2 from here and draw a double bond. So in this case, no lone pair on the central atom. This would be nonpolar because everything attached to the central atom is just oxygen. So the lone pair are on the oxygen, not the carbon. So this would be nonpolar. Okay, here is the last one. Got carbon. We have chlorine. We have fluorine. There are 2 chlorines. There are 2 fluorines. All right, so when I add these all up, I get 32. Carbon goes in the middle. Chlorine on one side. Fluorine over here. Bond everything. 2, 4, 6, 8. Fluorine and chlorine both need 8, so they're going to need 6. So let's go ahead and give each one 6. And then 6 times 4 is 24. So we will have used up all of our electrons. Okay, now this one looks symmetrical, but we have chlorine, and then we have fluorine. So not everything attached to the central atom is the same. So it looks symmetrical, but in order for it to pass that symmetry test, everything has to be the same. So this would be a polar molecule. And that is overall polarity. Now there is a different type of polarity, there's bond polarity, which is separate from this, but when we're looking at overall polarity, those are the steps to figure out polarity.